Hello everyone, my name is Alexey Kirillov. I'm a master's student of the Faculty of Computational Mathematics and Cybernetics at Moscow State University and work in the Yandex team focused on generative image models. Today, I'm excited to share my project, the IQA-Adapter method. As shown on the first slide, modern generative models are capable of creating stunning images based on textual descriptions. As the Excel which we worked with generates exciting pictures with various concepts. But there's a problem. We don't have direct control over the quality of these images. Sometimes we need a highly detailed image, whereas other times, for example, for data augmentation, we may want to deliberately distort them. This led us to wonder, can we teach a generative model to vary image quality over a broad range, from deliberately degraded to highly detailed? Let's quickly review what exists in this realm. On this slide, you see examples of modern diffusion models, which used to work with SDXL because it's open source and widely used. Many methods have been designed to control generation, as seen here. ControlNet allows generation control via depth maps and poses, while IP-Adapter uses reference images. However, these approaches mostly control content or style, not quality itself. In parallel, the field of image quality assessment is evolving. This slide shows examples of modern IQA and EAA models. IQA assesses technical quality, like artifacts and blur, while EAA evaluates aesthetic appeal, such as composition and overall impression. There are also methods for improving generation quality. Diffusion DPO uses reinforcement learning. Beautiful prompt refines prompt, and QRefine does post-processing. But they all merely maximize quality without allowing for wide range control. In real scenarios, different users need different levels of quality. Professional artists require hyper-detailed images. Regular users look for aesthetically pleasing images with a wow effect. For training and testing image processing algorithms, deliberately distorted images with specific artifacts are needed. Existing methods lack this flexibility. As you can see on this slide, our IQA-Adapter allows quality to be used as an independent conditioning parameter. Initially, we tried a straightforward approach, gradient optimization. At each step of generation, we compute how altering the image impacts the quality score and adjust the process in the necessary direction. Technically, it works by taking the gradient from the IQA model and adding it to the standard diffusion step. However, this method has a significant downside. Look at these examples. The model finds loopholes in IQA matrix. It generates odd patterns that score high on IQA matrix but appear completely unnatural. It's akin to adversarial attack in computer vision. Trick images that mislead neural networks but are obvious to humans. To address this issue, we developed the IQA-Adapter. Instead of direct optimization, we teach the model to understand what quality image means on a deeper level. The diagram here illustrates how this is done. The quality rating, e.g. 9 out of 10, goes through a projection model, transforms into qualitative tokens, and influences generation via separate attention mechanism, named qualitative attention. Crucially, we use separate attention layers for text and quality. This allows the model to clearly separate what to generate from how qualitatively to generate. We also added a mechanism called qualitative negative guidance. This mirrors the idea of negative prompts that steer generation away from undesirable outcomes. In our case, if we want high quality, we not only pull generation toward high quality examples, but also push it away from low quality ones. We also developed a version of our adapter that conditions the model on an image, the reference-based IQA-Adapter. This allows specific types of blur or compression to be transferred from one image to another without copying objects or colors. The diagram shows how this is done. The reference image passes through an IQA model. We extract activations from intermediate layers. These activations are projected into quality tokens. This influences generation via attention mechanism. We use the Arnica model specifically trained on separate quality information from content. Therefore, we can transfer, for example, specific JPEG compression artifacts without copying objects or colors palette. Training the IQA-Adapter is relatively straightforward. We use a regular dataset of image-text pairs, compute the quality rating for each image via the IQA model, and train the adapter to predict noise using both text and quality ratings. In our experiments, we trained the adapter on 3 million images from CC3M and then fine-tuned on a subset of Lyon with high aesthetic scores. The entire process took about 260 GPU hours on our NVIDIA R100. The first experiment demonstrates the effectiveness of conditioning on high-quality ratings. We trained multiple IQA adapters on different metrics and compared them to the baseline model and other quality enhancement methods. The results are quite promising. IQA adapter with topic gives an 8.7% increase in quality metrics. Combination of topics plus Lyon aesthetics 9.2%. Using qualitative negative guidance up to 10.1%. Here is a direct comparison. Look at the details. The left image from the baseline model and the right is from the IQA adapter. Notice the improvement details, sharpened textures, and enhanced colors. It is especially promising that improvements aren't only on metrics the adapter was trained on. For instance, an adapter trained on topic also improves Arnica and Club IQA+. This suggests good generalization ability. The main feature of our approach is the ability to control quality as a continuous parameter. Here are generation results of the same prompt at different quality levels. First percentile results to distorted images with artifacts and blur. 25th to low but acceptable quality. 50th to average quality, roughly equivalent to the baseline model. 75th to good quality with enhanced details, and 99th to maximum quality with sharp details. The graph shows that quality ratings mainly correspond to specified level, and the relationship is almost linear. The model truly understands what quality is and can regulate it. Objective metrics, despite their convenience, don't always correlate with actual quality. To more honestly evaluate model, we conducted a subjective comparison involving over 1,000 people. Each assessor compared two images generated with different quality conditions. A total of 300 different prompts were evaluated, gathering over 22,000 individual comparisons. The results confirm the effectiveness of our approach. IQA adapter with high quality wins over the baseline model in 60% of cases. Average quality roughly matches the baseline model with 51% win score. And low quality, as intended, loses with 21% win score. An important question is, does focusing on quality degrade the model's relevance or its ability to follow a prompt? We check this using the Geneval benchmark, which analyzes how accurately a model generates specified objects and their properties. The results are encouraging. Our adapters generally differ negligibly from the baseline model in the overall metric. An IQA adapter with hyper-IQA even improves some aspects: attribute binding and position, e.g. object placement. We also measured FID and deception score on 10,000 captions from MSQCO. FID improved on 6/10, indicating better alignment with the real image distribution. Our final experiment showcases the capabilities of the reference-based IQA adapter in transferring qualitative characteristics from one image to another. We use the Cadin 10K dataset, which contains 25 distortion types at 5 strength levels. Here are examples of transfer distortions. Unlike other methods, such as IQA-Adapter and StyleCrafter, our approach correctly distinguishes distortion types, for example, blur versus JPEG compression, preserve distortion level from weak to strong, and transfers only qualitative characteristics without copying content. Objective metrics confirm these observations. We see high correlation of IQA ratings between original and generated images, low clip image similarity with reference, confirming the absence of semantic copying, and high activation similarity in IQA models, indicating the transfer of qualitative characteristics. Reference-based IQA adapter can be a valuable tool for data augmentation, testing image enhancement algorithms, and artistic purposes. In this work, I presented IQA-Adapter, a method for controlling the quality of generated images across a broad range. Experiments show that IQA-Adapter improves quality at high settings and conversely can intentionally reduce it at low settings. Furthermore, the IQA-Adapter can be modified into a reference-based IQA-Adapter for transferring qualitative characteristics from one image to another. In future work, we plan to apply this approach for training super-resolution models and adapt to video domain. Thanks for attention, because attention is all we need.